In this problem, we're presented with what turns out to be a multi-degree of freedom system. The mass at the bottom is going to be able to translate up and down by a degree of freedom we're going to define as x, and we're going to see that the node between spring K2 and damper B2, defined by a degree of freedom y, is also able to move, and x and y can move independently of each other. So adding this spring and damper into our system is going to complicate our analysis a little bit, as now we have a multi-degree of freedom system. So ultimately, what are we trying to find though? We only care about, in this problem, one transfer function. We only care about tracking the output of the mass. But we're going to see with this solution procedure we're going to go through, as a byproduct, we could also find the placement of y in terms of time. So we're going to find what I'll call g is x over p. And then once we have our transfer function, then we're going to say that p is a step force magnitude 10, and we want to see what happens to the position of the mass as time goes forward. It's a mechanical system, so as before, we need to start with free body diagram, or actually several free body diagrams in this case. I'm going to start with a first free body diagram. You'll see why I'm drawing it down here in a second. That is going to be my mass. And then on the right-hand side, I am going to have the inertia of the mass. The mass has the ability to translate up or down only, no rotations, no side-to-side motion, and it is going to be defined by x. And again, we are provided with that degree of freedom, so I'll just stay with it. So x is defined as positive down. Now I want to put all of the forces that act on my mass m. So I'm going to see that it is directly attached to K1 and K2. It is also being affected by this force P of t. I'll start with the external force first to make sure that I include it here. So it is defined as positive down, so I have that P of t. Now I'll start with the left spring, K1. I am drawing it in tension, so I need to come up with what is its value such that tension is positive, compression is negative. Well, K1 is attached to the ceiling on top and X at the bottom. If I look at those 2 points it's attached to. So the bottom is X of t, the top is 0. So I only really have to worry about the X of t. So if X of t is positive, K1 is in tension. If X of t is negative, K1 is in compression. So positive X causes a tension in K, which means I want a positive K1 times X in this case. Right? So again, we want to stick with what value on the degree of freedom, positive or negative, puts it into tension. Here, positive X of t, so a positive K1X. Right, that spring was relatively easier. Now I have to worry about spring K2. This is now more complicated because at the bottom it's attached to X, but at the top it's attached to Y. Both the top and the bottom can translate. We've not seen that before. We did not see that in K1, but our thought process is going to be the same. And also as a note, I have this, what I call a node between K2 and B2, because that node is going to be able to translate independently of the mass. I can hold y at 0 and still pull the mass up and down, and that's perfectly fine. I can hold the mass still, and I can move that node up or down, and that's also possible in the system. So x and y are independent degrees of freedom, both dependent on time, but they can move independently of each other. I also want to note that this mass does not directly touch the damper B2. So the damper will not be in this picture. It does affect the mass indirectly, as we'll see through the equations in a moment. But in this picture, the damper isn't there because the damper does not directly touch M. I'm only seeing what directly has a force on M. So K2, that spring does. Now I need to be worried about the net displacement of a spring to determine the force in it. Because for instance, if x and y are both the same, let's say they're both 1 meter, That means the top of K2 goes down by a meter, as does X go down by a meter. So actually the spring hasn't stretched or compressed. It's just done a pure rigid body translation, which means that there should be no force if X and Y were equal to each other. It's when they're unequal that K2 is going to be compressed or stretched. Now, same thought process as K1, but I have to consider the bottom and the top separately. And I have to respect the direction of the degree of freedom's positive sense. So let's look at X. Let's hold Y still, set Y to 0, and then think, is a positive X or a negative X cause K2 to go into tension? Well, when Y is 0, acting kind of like a ceiling, a positive X causes K2 to go into tension. So positive X goes here. Now, kind of the opposite thought. If X is 0, if X is acting like a floor, then will a positive Y or a negative Y cause K2 to be in tension? Well, in this case, if Y is positive, it will compress K2, so a negative Y will stretch K2. Now, this is dependent on how the degrees of freedom were defined. In this case, we were given X positive down, Y positive down. If Y were positive up, that would change this equation. But as long as we're consistent and we make our inference the opposite at the end, that a positive Y is up instead of down here, being consistent will carry us through. And look also at what this does. If X and Y are equal, that we know should be a rigid body translation resulting in no force. And that's true here. If X and Y are equal, X minus Y will be 0, meaning there'll be no force coming out of that spring. So we want to pay particular attention to these relative displacements or relative velocities that are going to come up in multi-degree of freedom systems. So in this case, assuming tension in the spring, the proper value here is the K2 times X minus Y. And we have then the inertia here is going to be in the positive direction. Its mass times its acceleration. So m times x double dot. And the acceleration is always absolute, so it is just whatever its position is, the second time derivative of that. Now, I actually need a second free body diagram, though, because I also want a free body diagram of every node. So everything that can translate nodes and masses for mechanical systems need a free body diagram. The K's, the B's, we are going to always treat and assume they are massless, so we don't need to worry about their inertias, but the node does need a model. So the node is this dot up here. Now notice I'm drawing it above M so that I'm kind of exploding my view. It makes it a little bit easier to make sure I draw everything in the correct directions. Now what is affecting the node at Y? Well, it's directly touching K2, it's directly touching B2. I'll start with the B2. Now if we look at B2, the top of it is on a ceiling and the bottom of it is at the node. So this is more like how we did K1. So assuming tension, so coming out of our node, it's going to be B2 times Y dot. And now the force from the spring K2, drawing it in tension, so coming out from here. Well, actually, we already did the work. The force in it is K2 times X minus Y. So as long as we're always assuming tension, we don't have to do this twice. It has to be equal and opposite to what it was on the other half of the picture. So here it's pointing down, but with the same value, K2 times quantity X minus Y. Equals, all right, so now my inertia picture. So left side is done. The only forces that directly touch Y are the force from the damper B2 and from the spring K2. So that's all accounted for. Now on the right-hand side, my inertia. Well, it's mass times acceleration. However, a node has or is going to be treated as though it is massless. Thus, it has no inertia. So really, that dot on the right-hand side is the inertia picture. What I like to do, though, is to remember that I've already thought about it and I indeed want it to be blank, is I'd like to put a circle around it just denoting that, hey, I've accounted for this, there is no inertia in it. Because otherwise, if we see just a dot there, we might go back and think, oh, did we do this yet? The circle lets me know, yes, we've already done this, it's just that nothing is going on. All right, and those are our two free body diagrams, the node at y and the mass at x. We look at free body diagram 1, that's the mass, we have the forces that act on it and its inertia. Free body diagram 2, the node, the two forces that act on it, and it has no inertia because we treat it as a massless object or a massless point. Now we can write our equations of motion, one per free body diagram that we have. I will start with picture 1 here. I will sum my forces along that x direction. Oh, and I did forget up here to establish that y was positive down there. So now my second free body diagram is complete. I have that coordinate system. All right, so still looking at picture 1 at the moment. In the x direction, p of t is positive. It points down, and x is defined as positive down. And I have a minus k1x because it points up, and positive is defined as down, minus a k2 x minus y. And again, it points up where down is the positive sense. Equals, in the positive direction, mx double dot. And then I have my second free body diagram. I will call this equation 1, and this is equation 2, now that I have multiple equations that I have to be working with. So I will sum forces in the y direction now in picture 2. So I'm looking at the node. In the negative y direction, b2 y dot, and now plus k2 x minus y equals, now here it has no inertia, so the right-hand side is 0. Right, two equations of motion. What I want to do is now I want to take the Laplace transform, because where I'm going is the transfer function x over p. Now I have two dependent variables. I have x and I have y, and I have my input, which also is a dependent variable, but it's an input variable, p. And we'll see how this starts to work out. So I am going to, actually first, I'm going to make equation 1a, where I am going to say p of t minus k1x minus, and now what I'm going to do is distribute the k2. I think it's a little bit easier when then we, in the next step, are going to take its Laplace transform. So in 1b, I'm going to take the Laplace transform. So p of t, well, the Laplace transform of p is going to be capital P of s. I'll put the s here for now. Minus k1, that's a constant, times x, minus k2 times x plus k2 times capital Y equals ms squared times big X. All right, so notice we haven't seen this before. I have x, a dependent variable, and y. Again, the Laplace transform of little y is just big Y. And I have my input p. I had initial conditions of all 0 because we were told we started at equilibrium. So that x of 0, y of 0, x dot of 0, y dot of 0 all went away. That's why this came out pretty clean here. So in 1b, I have x, I have y, I have p. This is where, again, I need to track my outputs and my inputs. So outputs, I have x and I have y. And I only have one input into my system, and that will be p. And I'll put a little loop on here to denote, to make sure we remember this is capital. Now the rule is going to be, I am looking for as many outputs as I have equations. Right now 1b is my only equation in the S domain at the moment. 2 will get there, but 1b is my one unique equation, but I have 2 outputs. Because remember, where do I want to go? I want to find x over p. And the rule is for a transfer function that the right-hand side can only have things with s on the top and on the bottom. And at the moment, if I tried to do that with 1b, y is going to be on the right-hand side, and that's not allowed. So I'll be able to substitute it out with another equation. So that's why I need to keep going and now look at equation 2, which I will rewrite also first as 2a, where I will distribute out that k2 term, so plus k2x minus k2y equals 0, and then make 2b, where again that's going to be the Laplace transform of 2a, so a minus b2s times y plus a k2x minus a k2y equals 0. Two outputs, x and y, and now two equations, 1b and 2b, I am now going to be able to get x over p. And actually, I will also be able to get y over p along the way. And we'll see that we were not asked for that, but we're going to use Mathematica to do this, and it's going to give it that, it'll give us that value regardless of whether we wanted it or not. So I'm going to go and solve this in Mathematica. But I'll talk first about how would we solve this by hand. Well, if I want to solve this by hand, remember the problem with 1b is that if I want x over p, I'm going to have to get rid of that y. So by hand, I could take 2b and solve it for y equals something times x. Right? So it's going to be some fraction with s's in it. And what I could then do is take that and substitute that in for y in 1b. And now I would have an equation that has only x's and p in it, and then I can get out from there x over p. Now this is relatively simple because there's only two equations, so I only have to do one substitution. But even doing this one by hand is kind of a chore, so I will demonstrate how we do it in Mathematica and let it do the algebra for us, because really our mission is to get the transfer function, not to show off that we're good at doing algebra. All right, so in Mathematica now, I'm going to establish, I'll call it EOM1 for equation of motion 1, and this will be my 1b. So here I'm going to have my p minus k1x minus k2x plus k2y double equals ms squared. Okay, so I did type it a little fast, so just to make it clear, there is a space between k1 and x because that is going to be, Mathematica knows that that means I want multiplication. I could explicitly put a times there as well, which I'll do for now, just to make it clear what I'm doing. And then the same thing here, that is m times s squared, and then we're good to go. All right, so I just want that input, and I will suppress that for now. Now I can put in my second equation of motion, the 2b. So EOM2 equals minus b2s, I'll put the times in there, times y, plus k2 times x minus k2 times y double equals 0. And I will run that. All right, so now it has stored EOM1 is this equality and EOM2 is this equality. I've stored two equalities into variables, EOM1, EOM2. Now I can let Mathematica do some algebra for us. So I can tell it to solve. And now I have a list of two equations, EOM1, EOM2. Notice these are in the curly braces. And now I do have to explicitly put what I want it to solve for, because remember, I have three variables, x and y and p, but here I have to put my outputs, which again I noted above earlier, my outputs are x and y. So x and y go here. What that's going to tell it to do is isolate x equals something and y equals something, but x and y will not appear on either of the right-hand sides, as we'll see in a second. And we kind of get this a little bit of a mess here. And I made a little bit of a flub. I forgot in equation motion 1 the x there. So that's why it didn't come out quite right. Now it looks correct. All right, so notice I have in the solve, I have x equals some stuff, y equals some stuff. I have this double bracket. I do want to get rid of that just really for aesthetics. All right, now I don't quite have my transfer functions yet because I have this p on the left-hand side. So what I can do now, I will do this manually. I will say gx is, and what I can do is I can really just copy and paste. And what I want to do is effectively divide out by the p. So I'll just put a comment here of what I did. So gx is my x over my p. So I kind of manually divided through by the p, and now that's why it left. And notice that it was p times this stuff, so I can just divide through by it. All right, so that's my gx, and I will save that. And I will also, while I'm here, I'll do the same thing for the gy. So I'll copy this y term. I will divide through by the p, and now I have my gy, and I'll just save my comment here because it's going to be similar that gy is my y over p. All right, so I do have these two transfer functions now, gx and gy. For the purposes of this problem, I only care about, though, the gx, because that's the x over p that I'm trying to get to. Now I need to manipulate it a little bit. If we look at it, it's not quite in the form that I want. I have an s cubed, I have an s squared, I have a bunch of s terms, and I have a constant. And I have an s on top and a constant. That's not too bad here, but I want to write this in a standard form where I have coefficients, a single coefficient in front of an s cubed, squared, s, and a constant. So what I can do is actually rewrite this and say collect numerator. So take just the numerator of gx and then collect the s terms together. And then the same thing for the denominator. And we see that it formats it in a nicer way. It has now grouped together those two s terms with a single coefficient in front of it. And that's going to just make it easier to write down in the end. Now, why does this matter? Well, when we go into MATLAB, remember, we need to put in the coefficient in front of the descending powers of s. So if they're already grouped together, that's going to make our lives a lot easier. And I'll call this gx2. And I could do the same thing for gy. Again, I don't, in this problem, need it, but I already have most of the information. And notice that the denominator for the transfer function x over p and y over p, the denominators are actually identical. It's the numerators that are different. So this is what I came for. This is what I wanted Mathematica to do for me, was get me here. This is x over p. It's not quite in the format I want it, which I'll show in a second, because it's ascending powers of s by default, but I'm going to rewrite that anyway by hand. But this is how I can use Mathematica to do the work for me. I took the two equations of motion in the frequency domain, and then did the solve command to isolate my outputs. I then had to manually get rid of that input by effectively dividing through it, and then I let Mathematica do a little bit of the algebraic cleanup by using that collect, which is going to collect coefficients in front of the variable that you specify, here s. And I have to separately do the numerator and the denominator. All right, so I'm going to take this and I'll paste it into my OneNote, and I want to rewrite it. So g is my x over p, and I want to write it in the correct format. So I really just have to reverse everything. So that's going to be b2 times s plus k2 is my numerator. And then in reverse order, I have my b2m s cubed plus k2m s squared plus that quantity b2k1 plus b2k2 times s plus k1 k2. That now, properly written, is my transfer function from my input p to my desired output x. Again, if I wanted to, I could have also written y over p, that transfer function, and that would be useful if I wanted to track the position of that node. In this problem, though, again, I did not need that. And I just want to point out, again, I have one coefficient in front of the s cubed, one in front of the s squared, one in front of the s, and then a constant. And when we go into MATLAB in a second, we'll see why that's useful to us. Always descending powers of s in the numerator, descending powers of s in the denominator, and those single coefficients in front of each of those terms. So the s cubed should only appear one time, the s squared one time in the denominator, the s one time in the denominator. That in this one is where we had to group them together, and then that constant term. So at this point, we have finished the first part of what we wanted to find, was that transfer function. Now, let's see what happens if we introduce a step force of 10 newtons as the value for p. And then we can compare it to what happens if p were an impulse, if we just hit it with a hammer and then stopped, rather than the step force that is going to turn on and be that constant 10 newtons, and it's going to stay on. Right, so what we're going to do is take this algebraic form of our transfer function and apply those parameters in MATLAB. In MATLAB, I start by putting in the values of the parameters that I was given for m, k1, k2, and b2 from the prompt, and they were already in base units, kilograms, newtons, meters, seconds, so I just am going to stay with those base units here because that's what I want to be operating in. So I'll put those into my workspace. Now I create the transfer function. Here I have exactly what I had written down by hand that came out of Mathematica. And again, notice the format it wants is descending powers of s. So in the numerator, I will have, well, I'll go right to left, constant term, s term. And then for the denominator, the constant term, the s term, the s squared term, the s cubed term. So I will run line 25 and then print it. So that again, we can just verify that it did do this correctly. Yes, we have an s on top and a constant, an s cubed, squared, s, and a constant on the bottom. So g has been input correctly into MATLAB. It's the right form that we were looking for. So those descending powers of s are crucial. Now, just to do an investigation, again, this gets into what we're going to be interested more in Unit 2, the analysis portion. We're at this point done with the modeling step, that Unit 1 stuff. We have our transfer function, or state space model that we'll talk about at the end of Unit 1. But for here, transfer function. Now we can use it and simulate what happens if we put a step input in for a 10 Newton step function. Right, so like the previous example, I'm putting step 10 times my transfer function, and what it's going to output is, in this case, x, whatever the output is of that transfer function. The input was that p. Here I'm using a step function for p. The output is x. So let's see here what that looks like. I did not do initial value theorem, final value theorem here. I could have to verify somewhat what I'm getting from MATLAB. But again, it's just going to tell me what happens at 0, what happens at steady state. It doesn't tell me what happens in between. This numerically is telling me that information. This is the step input. We are starting at 0, and at steady state, we are at about here 1.67, so 5/3. That's happening by chance, just by the parameters that we chose. That at steady state, 5/3. And in this one, initially it's at 0. We apply that step. It goes up to a peak of 2.53 meters. Again, that's probably a lot for this system, but that's how the numbers work out. And then it comes closer to the equilibrium point, 1.11. Then it goes less far away than the first time, and then that keeps happening. And this is because we have that damper that is dissipating energy out of our system. And eventually it's going to come to the steady state that is below that initial equilibrium point, which was x equals 0. It's now below it, and it's at 1.67 meters below, in that positive x direction, the equilibrium point. So we have these oscillations around the new equilibrium point when we apply this step function. Let's see what happens if we apply an impulse. So same magnitude, kind of. It's 10 units still. Now it is different. It is a different unit because it's an impulse rather than a step. But we can still see generally how is the behavior going to be different. So in a second figure, I am going to, with that same step, transfer function, apply impulse instead of step. So it's making p an impulse function in figure 2 rather than a step like it was in figure 1. And see what that looks like. All right, so basically at time is 0, we smack it with a hammer and then we let go and see what happens to it. So at time 0, we hit it with the hammer and we see that it goes down to an amplitude below the below the horizontal, 10.8. Now again, the magnitudes of the step and the impulse don't really align because there are different types of units here, but we still see it goes below the equilibrium point, it goes vertically downward. But then it's going to reach that maximum and then it comes back up. It's going to overshoot the equilibrium point of 0, and now it's above that horizontal, that original equilibrium point at 6.4. And then it goes back below it, back above it, back below it, back above it, and eventually for the impulse, it's going to come back to that original equilibrium point of 0. So we can look at them side by side for the general difference in their behavior when we hit it with the step versus the impulse. The step function is going to reach a new equilibrium point. In this case, it comes out to 1.67 because that unit step function turns on but never turns off. In contrast with the impulse, we hit it with that hammer, it responds to it, but eventually all of that new energy is going to be dissipated by the damper and it comes back to its original equilibrium point. To recap what we did, we were presented with this multi-degree of freedom system where we have a node at y and a mass at x, which are able to move independently of each other. It's a mechanical system. We wanted to then make a free body diagram of all the nodes, all of the masses. In this case, one node and one mass. We had to be careful on, in this case, the spring K2 that was shared between the mass and the node, because we need to make sure that we are putting in relative displacements of springs, and the same will be true with dampers. In this system, the damper, though, was attached to the ceiling at the top and y at the bottom, so it acted like the dampers we've seen before. But on K2, we had to pay particular attention there. From these two free body diagrams, since we're interested in finding one transfer function, x as the output, p as the input, we need equations of motions derived from these two free body diagrams. So summing forces in each of them gave us these two equations of motions, 1 and 2. I'm in the time domain, but I want a transfer function, which means I need to take the Laplace transform of each of these two equations of motion. So that gets me to 1b and 2b. I want to count up how many outputs I have, how many inputs I have. Two outputs, the position of the node y and the position of the mass x, and one input in my system, the force P. I have two outputs, and I have right now two equations, 1b and 2b, which means I will be able to solve these two equations for my two outputs. And that's what I did in Mathematica. I let it do the algebra for us. I solved for x, I solved for y, and then I was able to manually divide through by p to get two transfer functions, x over p and y over p. In this example, I didn't need y over p, so I did not record it, but I did find it. I cared about x over p. I transcribed it from the Mathematica output, which wasn't quite the standard form that I wanted, into the standard form I did want, where my numerator has descending powers of s and my denominator has descending powers of s, with only a single coefficient in front of each power of s. So this is the transfer function I then took into MATLAB to run the simulation on to see what happens to x if p were a step function or if p were an impulse function.